We are continuing our engineering basics discussion by talking about statics, and not the electrical kind, here on the K-12 Engineering Education Podcast. Hi, Sadhan.
Hey, Pius.
We're here for another episode of...
What is it called?
This is called... Well, this is the K-12 Engineering Education Podcast today, but I think that we're calling this Introduction to Engineering. Introduction to Mechanical Engineering, actually.
Yeah, so the idea is what we're going to do is we're going to pick each engineering. It'll be its own season. And in each of those engineering, we are going to look further into what are the different topics that this engineering field covers. And we'll talk a little bit about some of the most interesting concepts in each of those fields. Non-technically, as a casual conversation.
Like in real life.
Yeah,
right?
Where it's used. Like, what exactly is it about?
Yeah,
what do they learn about? And why it is the way it is.
Why the everyday person should care about mechanical engineering or electrical engineering or nuclear, whatever we're talking about.
Yes.
And it just so happens that in this season, we're focusing on mechanical engineering.
Yeah.
And we kind of talked about that in the last episode, why, and all the different things that go into it. And there's a lot.
Yeah.
And so today, we're drilling down on one specific topic.
Which is mechanics and more specifically statics.
Statics.
Yes.
In fact, that's a class that we both had to take in undergrad, I think, to get our
it's actually
degrees.
Something you learn even in high school physics.
Yeah, I wanted to talk about that.
Right.
It's like when I went to college and then we had to take a whole class on statics, I was thinking in my head, oh my God, do I have to take physics all over again?
Yeah.
Yeah, that's exactly what I thought. And I was like, ugh. But the true fact here, that class and the class right after, which is dynamics, which we'll talk about, statics and dynamics together made me think, oh, I majored in the wrong engineering discipline. I was majoring in bioengineering, and I should have majored in mechanical engineering because I really liked the classes, actually.
Oh,
yeah.
So you did the wrong major after.
No, I started as a bioengineer undergrad.
Okay.
And as a bioengineer, as any engineer, you have to take statics and dynamics and all these other classes.
Okay.
And I learned, oh man, I should have just been a mechanical engineer.
Wait, does do computer science or computer engineering?
You're right. No, they don't.
Okay, not every engineer.
This is why some people say computer scientists are not engineers, because they don't have to take all the same stuff that bioengineers and electrical engineers and everyone else has to take. That's
what
why
about electrical engineers? I don't see why this would be useful for electrical engineers, honestly.
Well, I remember, there are some things, like if you're designing chips, I do remember that when I was an undergrad, every electrical, mechanical, bio, and materials engineer, and chemical engineer, and civil engineer, they all took what they called core classes. And it didn't matter what discipline it was you were in, you still had to take statics. You also had to take Introduction to Circuits, and you had to take Introduction to Fortran or something.
Yeah, I remember we had to take, even as a mechanical engineers, we had to take electronics, simple stuff like how motors work.
Because we would use it, though. That was the argument.
Yeah. So we don't go as much in detail as actual electrical engineers, but we do go through simple circuits. I think that maybe that's how they go through it as well. But this is fundamentally physics. Statics is fundamentally physics. It's mechanics. It's about what a body is, like not a physical body, but any kind of.
Yeah, that's the joke.
Yeah. So that is a joke, right? So any kind of body, it's like anything that has a mass to it, we consider that as a body. And what are the forces acting on it? Is the forces making the body go through movement or not movement, stillness? So based on that, that's how we divide it,
the study of bodies.
Yeah.
Of things with mass.
Yes. Okay, there is another word though. We are also looking at, when you look at statics, we also need rigid bodies. So so when we look at statics, we take into account it's not only about the forces acting on it. The forces acting on it as a rigid body.
Rigid as in it's not like water?
Nor is it like a piece of rope.
Okay.
Now, a piece of rope has a mass.
Not flexible.
It can have forces. Yeah, it can be flexible. Now, the moment it's flexible, the field becomes study of materials.
Hmm.
So for now, we are only looking at the body doesn't really bend. It's not flexible.
Rigid.
It's rigid.
Hard. Well, maybe hard bodies.
Yeah.
Not mine. But
So-
yes, okay. You're bringing back memories.
Yeah.
These are
So
all
that's
the things.
statics. So it has to be rigid bodies.
Yeah. Why statics? Why is it called statics?
So my understanding would be, see if it makes sense to you as well, right?
Yeah.
So it's about all the rigid bodies that are completely, it doesn't have an acceleration. So, okay, the body is at rest. That's what it means when it's at static conditions, which just means that there's no movement happening in the body or between parts of the body.
So it can move. It's just not getting any faster or slower, right?
Yeah,
Like I could move at a constant speed
Yeah.
in space, and if there's no gravity pulling me in anywhere, there would be no acceleration.
Yeah,
Okay.
yeah. So it's like a car going at a constant speed.
Right.
So the moment it's going at a constant speed, we can assume that all the other forces acting is typically in equilibrium.
Uh-huh.
So when you say equilibrium, it just means that it's all balanced.
Yeah.
All the forces are, for every force you have an opposite force and it cancels out and becomes zero. So if it's either that or it's not moving at all.
Mhm.
There is there's not even a velocity. But in real life scenario, that's not even possible because the Earth is rotating and it's revolving around the sun, and the sun is revolving around the galaxy. So you're always having something happening.
So we're studying an unrealistic.
Unrealistic,
scenario.
but we are also talking about only in relation to something else, right? So I guess fundamentally the point is if it doesn't speed up or slow down,
No.
then
Yes.
it means it's in static conditions.
if its motion is going to continue on with nothing really changing it.
Yeah.
Okay.
Yeah.
I can picture that. I can
Yeah.
picture a car going at 30 miles per hour.
Yeah. So it's like at rest, but it doesn't have to be still.
Right,
Yeah,
right.
yeah.
You mentioned the word forces. That's also a physics word. And you said the forces are in equilibrium or they're balanced.
Yeah.
What is force?
Oh wow, that's a that's a deep question, right?
Yeah, I feel like we're talking about religion. Like you talked about, the balance of all the forces on our body. And it
That's like
instantly reminded me of a yoga discussion that we had the other day. But that's not quite the same thing, right? We're not talking about like emotional forces or spiritual maybe spiritual forces
Maybe, yeah.
for some people. We're talking about physical forces like the push and the pull that you feel.
Yeah. And how much you experience push and pull is proportional to how much force you're experiencing,
All right.
the magnitude of force. So let's say we place, what do we have? Let's say we place the laptop on the table. Okay.
This laptop that we're using to record this podcast is on the table.
Yes. And also a lot of people use laptop and they always place it on a table.
Yeah.
Now we can say that the laptop is right now in a static condition.
Right.
There's
it's not
nothing-
moving.
It's not moving unless you're trying to move the.
Well, it's not getting faster or slower, we should say.
Yeah.
It's not accelerating.
Yeah, the bodies of there's like two links. Any laptop will have like two rigid bodies that's
Two-
coming together as a in
Like
a
the
joint.
table is. Wait. You're saying the laptop itself is a rigid
Laptop itself has like this as a joint there.
Oh, where
Okay,
the monitor opens and closes?
Closes, yeah. So
Okay.
we need to consider that you're not trying to move that
So we're treating the whole laptop as a solid
one.
monoblock
As one,
that
yeah.
never bends.
a
All right.
L-shaped block. So it's open, it's there. You're not trying to adjust the screen, so it's already set. So right now there is the weight of the laptop itself that's pulling it downwards
Mhm.
because of gravitational force. So if it's pulling it, then there is a force that's acting directly downwards.
Pushing down. Yeah. Why isn't it crashing through the table here?
Right. So why do we consider it as in equilibrium? And we also know that the laptop's not going anywhere
Yeah.
because for the exact pull, the same amount of pull it's experiencing, the table is giving the push. So when they cancel out each other, the laptop is at rest.
It's in equilibrium.
It's in equilibrium.
So I heard you say that for one force, there was an equal and opposite force reacting to it.
Yeah.
That sounds like something that everyone has said. That's in pop culture.
Yeah. It's Newton's third law, right?
Yeah. One of the honestly, I don't remember. We can look that up.
Okay, it's the third
It's
law.
one of the. It's the third law. Thank you, Sadhan, for
so
knowing
it's like
this.
Equal and opposite. This is the most
Equal
famous
and
pop
opposite.
culture.
Yeah. They say that in cartoons, and
Yeah.
they use it as an analogy,
As a
to,
joke.
like,
As a
relationship.
joke too.
Yeah.
We use a lot of, this is all classical physics, right? So we use a lot of Newtonian equations.
I gotta just say, as an aside, I love how technical words end up becoming more poetry type words as time goes on.
That's true.
Like the whole phrase "equal and opposite reaction" that ended up being used by storytellers and stuff.
As it's even used as a joke, right?
Yeah, exactly. Or the word force, or the word gravity. I mean, gravity. Energy. Yeah.
Yeah, spiritual energy.
Right. This is part of the reason why there's confusion when we talk about this today, because people have co-opted technical words to mean more than just the literal thing. Like a force is not just a physical push or a pull. Now a force is, I'm attracted to someone, or it's pulling me to do something.
Or may the force be with you.
Yeah, exactly.
Pop culture.
Right. Actually, like, I wonder if someone's quantified the force in Star Wars.
Yeah.
Is it a push or a pull? I don't know.
That's not what we're talking about here. We're talking about more physical nature of force. But actually, that reminds me of another thing.
Yeah.
Einstein's theory of relativity.
Oh.
And that in pop culture, or everyday use, we kind of assume that I think he himself gave an example of, it's more of a jovial example, like relativity is something like 1 hour spent with the person you like versus 1 hour spent sitting on a hot stove.
No, that's true. That is ultimate relativity.
Yeah, that is experientially. Yeah, that's the idea of when he says time is relative. But I mean, it's a joke. It's not what the equations use. But just some little tidbit from what you said.
All right. Okay, so there's more to statics. We said that in statics there's balance of forces or equilibrium, and different physical laws like Newton's third law. There are different types of forces too. I know that you bring back those memories of my classes. There's like linear forces, things that push in a straight line. Like when we talked about our laptop here, gravity's pulling it down, the table's pushing it straight back up, opposite linearly aligned directions. But like, not everything has just two forces on it, right?
Yeah, exactly.
Like, imagine now this table that is in front of us. We don't have three people in the room today. No three-person podcast today. But what if all three of us were pushing on this table, like on all three sides, or maybe four people?
Yeah,
we've got one person on each side, and we're all pushing on the table.
It would move in the direction I push because I have the strongest.
Because you're stronger than everyone. Okay, there. So that's no longer static. Oh, well, maybe it's statics if you don't accelerate it.
No, if it's balanced.
If it's perfect. Oh, you're right. If it's perfectly balanced.
Okay, but I'm going to use a different example.
Yeah.
Okay, I'm going to go back to the same example of laptop.
Mm-hmm.
So you keep the laptop on the floor, on the table, and it's at rest because gravity is acting down.
Okay.
And the table is pushing it up, and it's canceling out.
So you got two forces,
Yeah. But why isn't the table sliding around? There is another thing that's happening there. It's not sliding around anywhere.
Like, because I can tell anyone who's listening right now, I'm reaching over the table and I'm pushing my laptop gently, and it's still not moving because I'm really weak. And
there is also some grips used under. But what are the grips doing?
Like that rubber surface on the bottom?
Yeah, the four knobs or maybe multiple.
Yeah. Well, I'm pushing it, and it seems like it's gripping onto the table and stopping me from
moving it.
From moving it,
so it's continuing to be at rest.
In fact, I'm pushing it, and if I push hard enough, it will start to move. But you're saying that right now it's still a static scenario.
Yeah.
And here we've got a couple different forces on it. Gravity pulling down. The table's pushing back up on it. Now I am weakly pushing it into the side.
And nothing's happening. It's not sliding at all.
So I believe it's friction.
It is.
Pushing back.
Right.
All right.
It is friction. So, but there is a limit to what the material can offer in terms of friction. When the force is higher than that, it'll start sliding.
So we need someone who's stronger to push more. So then you should push it a little bit more and see if we can overcome.
Oh, we don't want to make any noise
We'll
on the
screw
mic,
up our sound.
right?
Okay,
Yeah, so let's
we'll
not do that.
let it be. It'll stay
Let's keep it in the
static.
imagination level.
Okay.
So there was another thing I realized in terms of the laptop example itself. So we did talk about how the two parts, the screen and the keyboard, is connected at a joint. And let's say you move the screen itself all the way, not all the way. Let's say you move it. Oh yeah, so when you try to move it a little bit, it doesn't move much.
Okay.
But it's generally easier to change the angle of the screen.
So I'm bending the screen, the monitor.
Yeah.
It's like 90 degrees open right now.
Okay, so let's say if you open it further and make it
Now it's like 120 degrees open.
Yeah, let's say it's 130. But it's at 130, but it has stopped moving. It's not completely falling down.
Right. When you stop pushing it, it stopped moving too.
Yeah.
So we got another static scenario. I can see it right there.
Yeah. So we can call that moment, the force that you're applying. Now, okay, so let's look at it this way. So when you use your finger and put it on top of the screen,
right, where my webcam camera is, right?
When you push it, it's a lot easier to push.
Let's see. So I'm pushing on the outside. Oh, yeah. It's almost
easier.
tipping over my laptop.
No,
if
I'm going to hold the bottom.
So I'm going to pull it back towards
It's a lot easier, right?
Right.
Now, let's get half the way on the screen, on the side.
So I'm going to do something that you shouldn't do and push in the middle of the laptop screen.
It's harder.
Yeah. Let's not do that.
Okay. And you go further lower, all the way to the bottom of the screen.
Yeah, that's ridiculous.
That's a lot harder.
Right.
Okay, so what is happening here, the further away you move from a joint, it's a lot easier to move it. And we call this entire thing moments.
So if we're trying to rotate a rigid body around some kind of axis, some kind of joint, when we apply a force perpendicular to that radius, I'm using a lot of terms here.
Yeah.
I'm like,
no, it makes sense. Like you're pushing it away or towards.
Yeah, like when you open a door, you put the handle on the like furthest away from the hinge because who's going to open a door with a handle close to the hinge?
Yeah.
You pull perpendicular to the plane of the door because that's the easiest direction to rotate that door. So it sounds like we have an equilibrium of forces when it comes to a rigid body just moving in a direction, but we also have an equilibrium of moments, an equilibrium of a body rotating. Yeah. Like that laptop screen is no longer rotating. It's an equilibrium both in rotation and in linear motion.
Yep. So all the forces are canceling out each other. And there is also friction that's acting on the joints, but they are all canceling out each other. It's not speeding up or slowing down. When the net force or the total force, when you add all of them together, the opposites cancel, and then it comes to zero.
Okay.
So that's pretty much what static is.
Studying these forces applied in different directions.
Forces,
stopping the rotation, limiting the rotation, limiting the change in rotation.
Yeah.
Limiting the change in the velocity, change in the motion.
Sliding.
Yeah.
So all of that
Sliding,
together.
that's right. Yeah. You know, the example they would always give in both our physics and mechanical engineering classes regarding statics were like these impossible scenarios of, two people are on a giant ice skating rink and they're pushing each other. And like, it was always these scenarios that don't really happen in real life because that's the only way you can study it in class. You got to come up with an ideal scenario that is so uncommon.
Wait, I've never heard that ice skating example.
Well, like where you have a frictionless table.
Okay.
And we put a laptop on this frictionless table.
Okay.
And if I push on one side, it'll just go. But if you have someone else pushing on the other side, it'll balance out.
Oh, okay. So in the skating rig, two people are pushing each other and they're
It's just the idea of getting rid of friction, getting rid of any kind of reality. Like I was just thinking that, what was I thinking? Like when you were talking about the previous example with the moments and everything, in real life, objects have all sorts of moving parts. Like our laptop is has got at least, two rigid bodies connected by a joint, and then our own human bodies are connected, with all these things and soft joints and whatever. And I remember thinking like, oh, my teachers would always simplify a real life scenario down to something that could be represented with the static situation. Like my body has all these joints in it, right? And it's soft and it's squishy. And like I'm accelerating right now as I move my hands, but like my physics teacher back then would be saying, oh no, I'm just going to represent you with a single coordinate point. And gravity is being applied right on that single point. And then the equal and opposite reaction from my chair is being applied on that single point. And that's all you have to worry about. You don't have to worry about anything else. And it just makes me think, oh, engineering is all about simplifying things to unrealistic situations.
Okay, I wouldn't call it unrealistic.
I know. But like that's the surprising thing.
Yeah.
It may be unrealistic for some people to talk about, but it actually is realistic enough
for designing things.
For designing, for calculations.
Yeah. It's like very, very useful. So I guess when would you need to know about the moments we were talking about forces canceling each other, or we don't want friction happening. We don't want whatever building to deform or to bend, So where exactly would something learning about all of these different forces, learning about all of these loads that can happen? So we were talking about forces here. So we can also say force is equal to load, or instead of me using my hands to push it, if I throw a ball at it, or like if we put a weight to move it, it's still the same thing, same force. That's newtons. In newtons, it's happening.
Sure.
So the question is, where is it applied?
Right. Yeah. In reality, what do we care about statics?
Yeah. Why do we need to learn about all these small details that seems seemingly so abstract?
It seems like it. Yeah. But you got a point. There's actually lots of places where it comes up.
Yeah.
And you said a couple of them. Buildings. I mean, they shouldn't move a whole lot.
Yeah.
They should be static. Mm-hmm. Otherwise, the building might have some issues. Yeah. So you might want to do some calculations on the statics of every beam in your building. Make sure that all the forces are balanced on there.
When you're building, obviously the foundations, where the beams are here, the structure that holds the other parts, like the cement, the mortar, or the wooden floors in place, is actually the steel beams that you install in the first place. Now we can call this the framework for the building. So that's one major applications in terms of why we understand bodies at rest and what happens to bodies at rest when the forces are acting on it. It's because of this specific thing. If you want to continue to make them at rest, you need to understand all the forces acting on it and how we can oppose these forces acting on them. Mm-hmm. So it's continuous being in rest or continuous being in net force of zero.
We had an example right at the beginning.
Yeah.
Whenever you have a moving object that isn't changing in velocity, whenever we drive down the road, and I drive at a great constant velocity all the time on the highway. Like I'm always at,
it's awesome, right?
Yeah, I drive at 70 miles an hour and there's no deviation from that. And so if you were studying that scenario, the forces on my car are at rest. Are in equilibrium.
Yeah.
If I use the phrase correctly. Yeah. It means that my engine is applying some kind of force so that it goes on the wheels and the wheels push my car forward.
Yeah, I think you can experience it like if you're sitting in the car, you can experience it like
when you hit on the gas.
When you hit on the gas. When you hit on the gas, it feels like you're being pushed back.
Yes, it's called an accelerator. Yeah, of course.
Yeah, acceleration.
You're applying acceleration. Yeah. But when you take your foot off the accelerator and you don't do anything, you just slowly...
If it's moving at, say, okay, let's start with 0.
Yeah.
And you kick the pedal or the gas. You push the gas and till it reaches 30, you feel like your body is being pushed back.
Right.
Because it's moving forward and your body's at rest. So it's trying to push back on you. And when you apply brakes, then you move forward when this car is stopping. So relative to each other, one is at rest, one is in moving. But then when you're going at a constant speed and you're in the car, you both your body and the car is moving at the same velocity. or moving at the same speed. So you don't really feel any motion. It's like you're sitting in a room, other than the bumps on the road and the turning that you make. If it's a straight road and just going, you don't feel anything. It's like you might as well be sitting in a completely flat office place, or you could be sitting in a bedroom.
Right.
But I think in application-wise, building is definitely one of the best examples.
Because also the cool thing about the building example is that your forces in that situation, they're not applied to a single point.
Yeah.
Like I was talking about how maybe in the car, we're just talking about how the forces are all applied to our body alone. Or in this chair, I'm just modeling myself as a single point on this chair. But like with the building, a beam, you have forces across the entire beam at the two ends, and the forces are spread out. So you have to worry about how it rotates as well. And so it's kind of a cool problem to think about that in a statics scenario. Like you got to think about, how do all these forces on every single part of the beam cancel out? I think that's cool. Actually, that was the part of engineering that made me more interested in mechanical engineering when I took that class. It was the problem solving aspect of, okay, I've got this more complicated object and I'm pushing and pulling it in different ways. How can you add a certain force just to make it balance out just right so that it stays put? Or besides buildings and beams, you might think about bridges. It's the same deal.
Oh yeah, bridge is another great example.
Because you apply forces not just on a single point on a bridge.
Yeah.
I mean, you have 100 cars on the Golden Gate Bridge in San Francisco at any one time.
Yeah.
Every single one of those cars is applying, a ton of force at a different point on that bridge. And then you've got the different, pillars coming out from the earth and the water.
And also, it's not like all the cars are... it could be trucks which are like 10 times as much as a car.
It's not a uniform load.
Yeah.
It's a very,
distributed, varying loads.
It's the opposite of uniform. Random, I don't know.
No, it's okay. So
non-uniform. That's
non-uniform.
the opposite.
That's what we use as a technicality here.
Yeah.
But randomness is in everyday usage. But usually it's a varying load.
You got to design this bridge for
a lot
different
of
types
conditions.
of loads.
Yeah. So trusses. Trusses is another thing that's great. So if you look at some of the bridges, if you look at the bottom of the bridges, they'll be like this triangle shapes.
Yeah.
Different triangle shape, upside down, pyramid shapes. So from what we have learned on how different shapes behave in terms of different load conditions, we have found that triangle are the best, especially in the bridge case scenario. They're the ones where you can use minimal material. You don't need to use... You can think about it like, okay, what if I use a solid iron for the entire bridge? Right? One, it's incredibly difficult to manufacture and install.
A giant block of iron, is that what you're saying?
Yeah.
So instead of the Golden Gate Bridge, we would just have a giant cylinder of iron.
Yeah, imagine that. That's going to be terrible design, right? Okay, I'm not sure which one is golden. Is the San Francisco Bridge?
San Francisco, that red one from Full House.
Oh, yeah. Okay, I don't know what Full House, but I remember what you're talking... I know what you're talking about. But... I think I have the perfect example to understand trusses or a certain level of framework that comes from understanding statics is the cranes, or the cranes, construction cranes. If you look at them, you'll see that they're small triangle shapes.
Oh yeah.
Now imagine the entire thing solid metal. Okay, that's
a good.
Yeah,
that's not going to stay up very long.
It weighs so much.
Yeah.
And some of these beams are even hollow. So we were able to do that only because we understand statics. Because we understand what shapes, how forces affect different shapes. So without understanding that, we would have never come up with a design. So right now, that arm, instead of weighing like 50 tons, it weighs 1 ton.
Right.
That's 1/50th of the weight.
Yeah. And I mean, I don't know if you heard recently when one of those cranes fell down somewhere.
Oh.
Like, even though it's a lighter weight crane with truss, it's still heavy enough where it causes lots of damage and, kills people. So you can imagine we are preventing a lot of disasters by making most of our cranes lighter weight out of trusses and using statics to calculate it.
And also, even if it weighs so much, imagine if it's made of solid iron, steel, how much power do you need to move it around?
Yeah, no. And money.
What kind of motors will it be?
Yeah.
So that's where it's useful. So to understand how bodies at rest, how they behave when different forces are acting on it. and how can you continue to keep it in rest, and what are the shapes that aid in doing that, is all that we learn in its core abstraction in statics.
Do you think that people who lived 10,000 years ago knew about the calculations to in statics, like the stuff that we learned, like the people who built the pyramids? The pyramids are static.
Yeah.
There's an equilibrium of forces there at the end. I wonder what they did. Was it just guess and check?
I don't think they did guessing work. I'm sure they had enough evidence.
Maybe it was an empirical thing. It's not like they calculated it using equations that we did, but
I'm sure there was some calculations involved. Maybe not a static calculation, but I mean, it has to be mathematical. If you want to build a perfect pyramid, with the construction,
there's something.
I'm sure they use mathematical
geometry and all these
geometry to do
maybe
that.
Not all the things that we use, but they must have done something.
Yeah. Engineering start with the wheel, when they first invented the wheel, right? So that's still engineering. Or when they first found a way to wheels is one big technological advancement, but it also has something as simple as learning to plant trees and grow so they can settle down. That's an agricultural technology. It's engineering. We have agricultural engineering.
When there's this systematic study of this natural phenomenon.
Yeah. How can we make something work so that we don't put as much effort?
It strikes me that, we're talking about statics, which is the equilibrium of physical forces and moments. But the idea of equilibrium in general is so constant across the different fields of engineering.
Yeah,
we're talking about mechanical right now, but there's this idea of balance in
the civil engineering,
in civil engineering, even in bioengineering. My field, there's a class, all about biological equilibrium,
right?
Like the chemical equilibrium between the cells, the inside of a cell and the outside of a cell. Like everything has a certain way of making things stay constant. I think the word in the bioengineering thing is homeostasis for your body.
Yeah.
Like to keep all your chemicals and body temperature and everything constant, you need to have a certain balance of chemicals in you. And I guess in that same sense, for objects to be in equilibrium, you got to have that certain balance of forces.
Yeah. I think the best example I have to emphasize equilibrium is the sun itself, or stars. Any stars that you see right now. There's two forces acting, and obviously I'm generalizing this a lot. But
so this is forces in the not in the push-pull sense.
Oh, it is in the push-pull sense.
Oh, really? Yeah. Okay.
So in the push sense, at the core of a star, I'm gonna talk about suns, and let's just talk about sun itself. So anything that's like sun is a star, right? Yeah. So you have what is happening inside is huge explosions, and by nature, explosion means moving outside from a center, the force of pushing away from the center, and this is happening because of nuclear fusion of hydrogen atoms coming together to make helium, and it creates a huge explosions, like tons and tons of nuclear, maybe a lot more, like an explosion happening at the center of the sun, which is pushing away everything outside. But then with the mass of what the sun is, you have the gravity acting towards the center. When they are in perfect equilibrium, when the gravity it cancels out the explosion, you get a spherical ball hanging in the middle of the space. It's the sun.
That's really interesting. Right? I didn't think about it like that. No, because now you have all these forces that are acting from the same direction. Like I think I was always using the example of me sitting in a chair where the forces are pointing at me, but now it's like a point, the center of the sun, and you have all these forces pointing outside in all directions, in a spherical direction, and then forces all pulling inside gravity in all directions. Yeah. That's really interesting.
It is. But if you take the balance out a little bit,
you get a supernova.
You get a supernova, or you get a black hole.
Oh yeah.
That's how they've described.
So we're in this special zone
of equilibrium where life can sustain.
So equilibrium is not boring, like I was first saying in the beginning.
Wait, you said that?
Well, I was saying basically that I used to think that the study of these types of physics problems and and these simple statics problems. I used to say like, oh, we're just studying simple cases that don't ever really exist. Like we're studying a laptop that's not doing anything, that's sitting on a table.
Right.
I'm studying an apple sitting on a chair. That's not exciting. We want to study the apple being thrown against a tree or the car hitting 3 other cars and everything moving. Well, what you just told me is kind of a counterexample. Not everything in statics is boring. Statics makes the sun exist. It lets all life exist that we know it. It's something special. My laptop sitting there on the table is special because it lets us do this podcast. It's not crashing to the ground because of gravity. And we have Newton's third law to help us ensure that the table is keeping it up. Equilibrium is special. Equilibrium in our biology and homeostasis is special so that we're alive. So I think that's why studying equilibrium and statics is good. So thank you, Sadhan. I have a newfound appreciation for statics.
That's awesome.
Not as boring as I used to think.
For equilibrium specifically, because that's where the sun comes and life comes into picture.
Yeah.
Awesome.
So what are we going to talk about next?
So we covered statics, which is part of mechanics, which is about bodies at rest. Now the question is, what happens to the forces? What happens to the body when it is accelerating? When it's speeding up or slowing down?
Supernovaing or black holing.
Yes. So we have the sun. Now we'll talk about black holes.
That's exciting.
And where the cells from your body itself came from. Supernovas.
When my body starts to overheat and then I die. Yeah, no, that's
the same concept, but we're not going to talk about that. We might.
Yeah, that's really morbid. No, we're not going to talk about that.
No, I think we should. We'll talk about it because we spoke about equilibrium and sun, we will talk about how black holes and all those higher molecules are formed in supernova. But then essentially we're going to talk about dynamics, which is another major field of mechanics in mechanical engineering,
where we get acceleration. Acceleration is no longer zero.
Yeah,
can't wait.
It's no longer zero. It's going to move. There's going to be a lot of interesting things that's going to happen.
This has been another special episode of the K-12 Engineering Education Podcast with the mechanical engineers Sadhan Satyasilan and yours truly, Pius Wong. Thanks for listening, everybody. Review the show, share the show, and send me suggestions on what's interesting to you in engineering education today. Special thank you to the supporters of this show on Patreon, as always, because your donations make all this possible. To find out more about how you can donate to the show and let me know that you're listening, go to my Patreon page. That's patreon.com/Pius Labs. And that Pius is not spelled like my name. It is with an O. So you can find a link to it from the website, k12engineering.net. Today, our opening music is called Soar, and our closing music is called Polar, both by the artist Chris Pop. You can find more music by Chris Pop on SoundCloud under the username ChrisPop99. That's Chris with a CH, or just check out the show notes for a link. The K-12 Engineering Education Podcast is a production of my independent studio, Pius Labs, in Austin, Texas, where I work on multiple education and engineering projects like this one. So until next time, thanks for listening. Couple post-show notes. This may be the final episode of the 2018 season. I've been super busy with teaching and actually doing some web development, not just for this podcast site, but in general. But besides all that, I wanted to talk briefly about some topic ideas for future episodes once I get the time to cover them. One of the beautiful things about having a podcast is that you're somewhat of a journalist and people will tell you things. They'll tell you their opinions about engineering and education and STEM education, stuff like that. And they'll tell you it even though they might not want to be recorded in front of a microphone on the record. A lot of people, especially a lot of educators, former educators, current educators, are not happy with how they're paid. You can see that in the news with the teacher strikes that have been happening. Next door to Texas in Oklahoma, there's been a lot of news about that. That happened in Washington State. It's all over the country. Here in my district, public school district of Austin Independent School District, there are proposals to cut funding, close schools in the public school sector. And that's not just happening here in Austin. And Austin is a rich city, by the way, I think. But it's happening all over the country. And teachers are mad about it. So all around, I know that educators are feeling the heat. And that's why they're leaving the profession when they shouldn't be. There are also like great signs that educators are going into the industry from other industries too. That they're going into the field, taking non-traditional routes to get certified. And that's interesting. I think maybe we might see that as a pattern to talk about in the coming years, coming months. And so these are the things on my mind. Teacher pay, the state of teaching and how people view teaching, whether in the technical professions or not, and the difficulty it is to hire diverse teachers and keep them there, to hire qualified computer science teachers, for example. So that's something that hopefully I can tackle come 2019, among lots of other cool things like toys and educational games and the cool stuff being done at the microbrewery nearby who has hired a chemical engineer to manage manufacturing of their beer. But these are all the things that I would like to cover. And I can't really do it without the support that I've gotten and with continued support. So thank you so much for donating that $1 monthly to those of you on Patreon. Happy 2018. And I hope it wasn't too problematic for most of you. I hope you enjoyed the good parts of it. And I hope that 2019 serves you very well. To all the teachers listening, good luck. Enjoy the winter break, and we'll see you in the spring.